Hello all. So in this video, let's discuss about the most important algorithm in machine learning, that is linear regression, and that too using gradient descent. Okay. So for understanding linear regression, I have taken a sample data set. So you can see here we have a sample data set where the task of this particular data set is to predict a salary of a person, right? So the target will be the salary, which is the continuous form, because regression itself means continuous form, right? So to predict salary of a person given experience, okay, given experience of the person. So we have to predict salary given the experience, okay. So let's try to solve this with the help of the linear regression. So whenever I say linear regression, the basic equation of a linear regression is, as we know, it is y is equal to mx plus c. So y is equal to mx plus c is the basic equation of a linear regression, okay, which is nothing but again a equation of a line, right? Equation of a line, okay. Now if I want to write this particular equation in this particular data set perspective, what we are trying to solve, we can write something like this. So y will be your target, whatever we want to predict, right? And x will be your input, right? X will be your input, and we'll talk about what is m and c next few minutes, right? So as I told, y is your target, so y becomes your salary. Y becomes your salary of a person. So you are trying to predict the salary of a person given experience, given experience. So when experience is given to us, we have to predict the salary. So we can clearly see that in this equation, if we are able to get this m and c value, if you are able to calculate or find out the m and c value, your job is done, your task is done. But how do you find out best MNC value? How do you find MNC value? So your MNC value depends upon your data set, what is given to us. Because your MNC values, we'll try to find out MNC values, best MNC values which fits your data, which actually fits your data. Okay. So let's understand this linear regression in terms of graphical perspective. It will be more clear to us. Okay. So let's assume I'm having a graph or something like this, a simple graph between your experience versus salary. So x-axis I'm taking experience and y-axis I'm taking salary. And let's assume this is your data points, which is on the graph, right? This is your, let's assume these are data points of various people with respect to experience and salary, which is a scatter plot, of course. Now, as I told you, this equation is talking about a line. When I'm saying that in order to find out the salary of a person, I have to find out the m and c value. The main target, the main idea, or the main goal of a linear regression is to fit a line, right? Because this equation is talking about a line. So to fit a line. But the point is, I can fit many lines here. If you just look at this particular graph, I can fit this line, I can fit this particular 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 line, any of this line. But out of these multiple lines which I'm able to fit, which line is actually a best line, right? Best line. So I want a best fit line, right? I want a best fit line. Out of this multiple lines, whatever I drawn here, I want a best fit line. Okay. And you should know that when I say this is a line equation, if I want to fit a best fit line, what do I mean by that? I want to find out a best MNC value. Because why? Why? Because you should understand that M indicates the slope of the line, right? And C indicates the y-intercept, or we can also call it as constant, or slope is also called as coefficient. Okay, let's understand this MNC values more clearly right now, and then we'll go back and understand how to fit a best fit line. If I say M is the slope of this line, what do I mean by this? Okay, let's assume you are able to fit a line something like this. Let's assume this is your best fit line. Now, what is this best fit line telling us? What it is conveying us? What is the information conveying us? What is this M conveying us? Is M, generally the formula of M would be something like this: y2 minus y1 by x2 minus x1. So what do I mean by this? For example, let's assume if I choose 2 points on this particular line, okay, this becomes your x1 maybe, this becomes your x2. For this respective x1 we have y1, for the respective x2 we have y2, right? So, and this becomes your slope, right? This becomes your slope. So what we are calculating here is slope tells us, generally if I talk about the general definition of slope, slope tells us change in y, change in y. So in our case, change in salary, because in our case y is nothing but salary, with respective change in, with respective change in experience, because in our case x is what, change in x, especially respective unit change in x. You should tell it as unit change in x. What do I mean by this actually? What do I mean by this? Let's try to understand right now. What do I mean by unit change? Okay. Okay. Let me take a small example, then you'll be getting a clear cut understanding. Okay. Let's assume right now you are having an experience of approximately, let's assume 2 years. Okay. Maybe after 2 years, your experience become 4, right? Right now you're having 2 years, and right now your salary is about maybe 50,000. And after 2 years, your experience become 4. Obviously, your experience become 4. And let's assume after 4 years, after 2 years, means at experience 4, your salary is right now maybe around 80,000. Okay, your salary is around 80,000. So you clearly know that you got an increment of 30,000, right? In 2 years, you got a hike of 30,000. Clearly, we can say. If I calculate the slope here, let's assume this becomes your x1, this becomes your x2, because you're talking about experience, that is x value, and let's assume this is your y1 and this is your y2. So your salary value will become your slope value will be something like this. The slope becomes, your slope becomes y2 minus y1, right? Y2 minus y1 by x2 minus x1. Okay, and if I just calculate this, it will be 30,000 divided by 2, which is 4 minus 2, which will be around 15,000. So if we just carefully observe what exactly this 15,000 telling us, what is the meaning of this particular 15,000? Is it talking about 2 years change? Is it talking about how much your salary incremented 2 years? No, no. It is talking about on average how much your salary got incremented for 1 year. That is what your unit change is. When I say change in y with respective unit change, in our case, as we are calculating your experience, in terms of year, 1 year is nothing but your one unit. 1 unit means what is, whenever you are calculating the slope, that is m, it is telling us, it is conveying us that how much increment on average per year in terms of this particular data set, or in generalized format, how y increases with respective unit change in x, right? Why I'm saying unit change? Because it's talking about only unit change. That is what your m is. So more clearly, if I just come back to this particular equation of y is equal to mx plus c, m is talking about if y changes this much, how is your x? It might be increase or decrease, whatever it might be. If y is changing so and so, how much x is changing? So it is more clearly, m is mainly talking about the relationship between x and y. It is mainly conveying us the relationship between x and y. That is what we are finding out in this particular m value, right? Next, coming to C, in this particular use case, if we talk about the C value, that is your y-intercept. Why it is called as y-intercept generally, or why it is constant, why it is, what is exactly C means? First thing, if we just substitute x as 0 here, just let's substitute x as 0, what happens? Your y will become equal to C, right? So the value of y when your x is 0, right? The value of y when x is 0, that is called as basically C. That is the reason it is called as y-intercept, right? That is the actual reason why we call it as y-intercept. So graphically speaking, if I want to talk about this graph and talk about this C, I can say the point where your line touches this particular y-axis, right? Intersect this particular y-axis. Here itself your x is 0, right? This is nothing but your C, right? So in our case, we can say that when you say x is 0, in our case, what happens? X is 0 means your experience is 0, right? When your experience is 0, means we can say that what is the salary offered by a company, or what is salary offered by this particular company of this particular data set when the experience of the person is 0, okay? That is nothing but your ultimately your C value, which is talking about your intercept. That is when experience of a person is 0, if this is 0, the value of salary means the initial salary, we can say. In our use case, it's the initial salary where your C is touching. So both M and C is conveying some information, right? So M is talking about how X is changing, how Y is changing with respect to X, means it is talking about the relationship between X and Y. And C is talking about the initial value or the intercept value, that is the starting point of your line, where your line starts from, right? That is when your experience is 0, okay? Now let's come back to the main algorithm perspective, okay? Now we understood what is M and C right now, how exactly M and C will be helping us to actually fit a line, right? Cool. Now let us come back to again a graphical perspective and understand the main idea behind the algorithm. As I said before, when I'm having multiple points like this, as I said before, I can fit any kind of line here. But which line would be best line, right? So a line, I would say a best line is nothing but, generally a best line is nothing but which is having the least error, right? Least error with your actual points, with your data points. That is nothing but your green points right now, which is having the least error. Means here if you just look at this line, or look at this line, by just looking at these two lines, you can clearly say that these lines are not best fit. But this line, maybe we can say it's a best fit. Maybe we can say best fit compared with these two lines. Why? Because these two lines are highly deviated from the points, right? Whereas these lines are somewhat fitting to your points and not that much deviated with your points, right? So that is what will be calculating in linear regression. You'll be finding out the deviation of your line from your points. How much your line has been deviated. How do we calculate that deviation? Okay. Let us take this simple point right now to calculate deviation. For example, this particular point. I want to know how much this point is deviated from your line, right? What is line? Line is like an approximation, right? Line is like an approximation for your respective X value. Means, for example, your experience is this. Maybe around here you have one experience value. The actual salary is this much, right? For this particular experience, actual salary is this much. But your line is predicting that this is your salary, right? So I can call this point as your Y actual point, and I can call this particular point as Y predicted point, right? Because line itself is your prediction right now, right? The point on the line itself your prediction. So Y actual and Y pred, and the deviation is nothing but your distance between this, obviously the deviation between this Y actual and Y pred, right? This becomes your error for this particular point, okay? If this line is too close to this particular point, error will be minimum, obviously. For example, for this particular point, we just take this particular point. For this particular point, the error is minimum, right? Very less. And it is almost 0 for this because it is almost on the line. So it depends, right? It depends from point to point. So how do you calculate the error? The error value will be your Y actual minus Y pred. Means you are finding out how much your actual point, that is your green color point, your actual point in your data set is deviating from the point on the line, deviating from the point on the line, which is called as bipyrate, right? And if we just carefully observe, for this particular point, this value can be negative, right? If we just consider y actual minus y pred can be negative, but can deviation be negative? No. So in order to solve this particular problem, we can apply square for this, right? We can apply square in order to solve the negative problem. We can apply absolute also, but we use square. I'll tell you why in later part. Why we use square when we have absolute, okay? But in order to avoid the negative values, because error cannot, because deviation cannot be negative, so we are applying square, right? Ultimately, we should find out the magnitude, not the direction, right? How much trend, how much deviation it is. Okay. Next, this is for single data point. Whatever I'm doing right now, it's for single data point. But here you can see in our data, we have multiple data points, right? Approximately, if you just look at your data set, approximately you have 30 data points here. If you want to calculate for all data points, the same thing you'll do for all data points and you'll add it up. The final point will become something like this. Final equation will be something like this. Summation of I is equal to 1 to n, where n indicates the number of data points, y actual minus y pred whole square. So this is an error, and obviously you will be finding out the average of this, because I want to find out the average deviation. I want to find out the average deviation. So if you want to find out the average deviation, you will divide by n. This becomes the average deviation. So if I divide by, you see what you are doing here, you are calculating, this is nothing but for single data point. So what I'm doing, I want to find out the same deviation for every data point like this. So whatever red color line I'm drawing here, that becomes your deviation line, deviation point from your actual point to the line, right? So I want to add up all the deviation. This becomes your error of this particular line, error of the above line, right? The error of the above line is this, is given by this particular formula. This particular error is also called as cost function in general. It is also termed as cost function. And this error is basically this particular error, which I'm showing you right now. This is called as MSE, which indicates mean squared error. Mean squared error. So what do I mean by mean squared error? Mean is nothing but what? Average. Are you finding out the average? Error, I told you the error. This is nothing but y actual minus y pred error. And we are applying square to avoid negative value. That is the reason it's called as mean squared error. Nothing but summation of I is equal to 1 to n. Mean means what? You'll add up and divide by n. Yes. So you're calculating the error. This is your error. You're squaring it to avoid negative values. So squared. You're squaring it to avoid negative values and you're dividing by n. This becomes your mean squared error. So ultimately this becomes your error of this particular line, right? Error of this particular line. But the point is, as I told you already, we want to find out the line which is having the best fit, right? The line which is having the best fit. Now, do you think this is a best fit? We are not still sure, right? Maybe we can draw one more line here. We can draw one more line here and find out maybe the one more best fit line, maybe here. Or we can draw one more line here. We can draw one more line here. We can draw one more line here. So any of these lines can be best fit. We are not sure about this. Any of these lines can be best fit. But out of these lines, which line would you think would be the best fit? Obviously, whichever line is having the minimum error, right? We clearly know that, because any of these lines can be having a minimum error. So ultimately, whichever lines is having the minimum error means minimum mean squared error, that becomes your best fit line, because that is least deviated from your data set and that is having a perfect MNC values. That particular line, obviously, because a line contains MNC, right? That particular line will be having the best MNC values, which will be helping properly to fit your data, right? So that the main target, the main idea, the main goal from now, whatever from our about discussion is a line which has minimum mean squared error, right? Which is having minimum mean squared error, that becomes your best fit line. and that particular line will be having the best m comma c values. If you are able to find out that line, then your entire linear regression is done. But how do you find out the minimum MSC? How do you find out minimum MSC? Here, if I just want to find out minimum MSC, or to find out the minimum line which is having the minimum MSC, I can do like this. Maybe I can take the I can do like this. Maybe let's assume these are data points. These are data points, right? And you start with some random line. Find out MSC. Again, one random line. Move that line bit forward. Find out MSC. Again, move this line bit forward. Find out MSC. Move this line bit forward. Find out MSC. Move this line bit forward. Find out MSC. Like this, I go on randomly moving my line. Means when I say randomly moving my line, what I mean by this? I'm randomly changing the MNC values, right? See, when I'm saying, if I talk about this in graphically, if I talk about this linear regression in terms of graphical perspective, I'm randomly moving the lines. But if I talk in terms of equation perspective, I'm trying to find out y is equal to mx plus c for random MNC values, some random MNC values. So like this, I'll go on changing my MNC values continuously randomly, right? I'll be going on changing this MNC values continuously randomly and find out a minimum square error. But do you think that will work? No, because it will take years to find out the best MNC values if you do like that. If you have a large data set, it will be taking very huge time. So what is the best way? The best way is to use a concept called as gradient descent, right? We use something called as gradient descent. So we'll use this particular concept in order to find out the minimum mean squared error, okay? And the gradient descent will work under the principle of your differentiation, right? Differentiation. We'll be using differentiation in order to find, or in order to apply gradient descent algorithm, okay? So now let's understand how gradient descent works for linear regression in order to minimize this mean squared error, right? In order to minimize this particular mean squared error. So in the last video, we already understood about how differentiation works. We understood that from the last video, the main points we derived is differentiation will be helping us to do two things. One is to find slope of a point on a curve that becomes your slope of tangent, right? On a curve that becomes your slope of tangent, right? And the second reason why we use differentiation is to find minimum or maximum of a slope, right? These are the 2 points which we learned from our last video in order to work with differentiation. Now exactly same points we'll try to use in order to implement this particular task, okay? In order to apply gradient descent for linear regression, okay? Now if I just come back to the linear regression minimizing point, we want to minimize the MSC value. And what is the MSC value? That is nothing but your summation of I is equal to 1 to n y actual minus y pred whole square divided by n, right? This is the actual MSC value, whatever we learned. We want to minimize this, okay? So we want to minimize this. If we just look at the graph, okay, if we just look at this particular equation, is it looking like something like, so it is looking like some x square equation. If I forget about this 1 by n, if I just take out this 1 by n, it's looking like x square equation. Let's assume this is x square, or maybe a square, some random, you can assume that this is the entire thing as a square, right? It's looking like a square, yes. And we know that your a square graph or x square graph from the last video, we understood that your x square graph will be something like this, right? Generally it will be something like this, a parabolic shape. Okay, let me draw it neatly. Somewhat. So where this is your 0 point, and this is how the equation will be. So exactly same way your your error equation will be. Now what we want to do is, the main idea of gradient descent is, you have to find out this minimum point. When I say minimum point, with respect to m and c, you have to find out the minimum point. Okay. So you can write equation like this. Okay. So the main important thing is you should find out the relationship. See, what is differentiation? Why we use something called as dou y by dou x? Why we use something called as dou y by dou x? What it tells us? It tells us rate of change of y with respect to change in x, right? Rate of change of x, or we can say like this in a better way, rate of change of x with respect to change in y, right? Rate of change of x with respect to change in y, this is the idea, right? In the same way, in gradient descent, in our gradient descent application right now, what we are trying to do is, as we find out, if you want to find out the minimum error, let's assume E is your error. So we want to find out what is the rate of change of error with respect to change in your slope. Because slope is nothing but your line, right? You're trying to change your line. So what is the rate of change of error with respect to change in slope? And the same way, rate of change of error with respect to change in your constant, right? These are the two things we want to find out, right? Rate of change in error with respect to rate of change of slope. And if you're able to find out that, you can find out the minimum point. Means what? If I talk about this gradient descent, how it works means, first you start with the entire gradient descent algorithm is something like this. Let me write out the steps of gradient descent, then you'll be having a clarity. In gradient descent, the very first step is you start with a point, random point, nothing but a random line. We start with a random line. Okay, start with a random point. So when I say random point, let's assume this is your graph where you have your all your actual points. If I talk in terms of graphical perspective, so you start with a random line. Right? When I say random line, random m and c value. Start with a random point, means random m comma c values. That is the very first step. Let's assume I have chosen one m and c value. Now, if I talk in terms of my error equation, let's take that like that here. Okay. So your error will be what? Summation of I is equal to 1 to n y actual minus y pred whole square divided by n. This is your error, right? Yes. Now I want to find out relationship between E and M, right? The main idea is this. The main idea of this one is this. That is what dE by dm is. So what I will be doing here is, I will be taking the error on the y-axis and m means you can assume that error is nothing but your f of x and this is your x, right? Error is nothing but, so what generally we do, y is equal to f of x, right? For this we'll be finding out the equation, the differentiation. So let's take m on e-axis, that is your slope on the x-axis, and e on y-axis. Okay, let's start with slope first, then we'll go back to constant. And we clearly know that your graph will be something like this. Because of the x square graph, we clearly know it will be something like this. So let me draw in exactly same way, like this, something like this. Okay, and this becomes your 0th point. We know that, right? Of course, this becomes a 0 point. Okay, now when you want to reach this minimum point, we know that this becomes your minimum point, right? Because the slope of tangent at this particular point is minimum, is 0. Basically the slope of tangent is 0. So wherever your slope of tangent is 0, that is nothing but d by dm is 0, and this becomes your minimum point of error. This, of course, you can see here the minimum point of error is this. Okay, now when I say I'm starting with a random point, let's assume your random m was this, whatever I'm putting in red, this is nothing but your random m point. Let's assume your random m point, this becomes your random m point, right? And for this m point, your error was some value. Let's assume this is your error value. For this particular m point, this is your error value. Okay. Now we can clearly see that when your error is this and your m point is there, when I want to reach a minimum point, means I want to go this direction, right? I should go to this direction. Okay. Now let's assume that my m value is this right now. Was randomly, when I'm choosing a random point, let's assume my m value was selected this. Okay. And my error is this. Let's assume this is my error for this particular m point. Now I should go to this direction. Ultimately, if your random point or if your m or if your error is at the left side, I should go to the right direction. If it is the right side, I should go to the left direction. This is the main idea, right? This is the main idea. Or more clearly, I should say that if your error is this and if your m value is this, I should decrease my m value. I should decrease my m value. In this case, I should increase my m value. I should increase my m value. In this case, I should increase my m value to reach the minimum point. In this case, I should decrease m value. So you can clearly know, already we discussed that the main idea of your gradient descent or the main idea of simple linear regression is to find out the best m and c value. So using this particular differentiation equation, you are trying to identify whether I'm trying to increase the m value or decreasing the m value and trying to find out the best m value. Maybe this is your best m value where your error is 0. Maybe this is your best m value where your not 0 but minimum where your error is minimum, your best m value. Maybe around some, I don't know, whatever value it might be, maybe 10,000 or 20,000, it might be anything, but I should find out the best m value where your error is minimum, that's a main goal. So here how do you increase or decrease, we'll see that now in 5 minutes, but we start with a random point right now. Let's assume it's starting with random point, right? I hope we got this point, how exactly this works. Now let's write down this in the form of steps, then we'll be having more clarity regarding this, right? Okay, so we will be having a random point. We'll be first choosing a random point, that is some m point, okay? And let's assume the error is I at this particular point, right? Now what we'll do is, the next step is, after choosing a random point on this particular curve, because that is what your line start with, it will start with a random point, and let's assume this is your point m with a respective error, okay? Now the next point is to find out the slope of that respective point on the curve, right? And how do you find out the slope? I am finding out the slope with respect to error, right? So it will become dE by dm, right? This becomes your equation because you want to minimize this equation, right? So dE by dm with respect to the slope, So we know that by using this, you can find out the slope of tangent. You can find out the slope of tangent, right? And this will be helping us to minimize your data, okay? Minimize your error. So the main point you should understand here is, here already with help of differentiating, we know that we can actually calculate the slope of the point on a curve, right? So that is what we are doing here. We are trying to calculate the slope of the point, right? How? For example, this is your graph, okay? This is your graph right now. And let's assume this is your random point on this one. You're trying to approximate a line here, right? You're trying to approximate a line here, and you're trying to calculate the slope of this particular line, right? That is what we have done in dE by dm. After calculating the slope of the tangent, that is dE by dm and of course dE by dc respectively, then what you are trying to do, you will try to, the third step is to update the m and c value. See, you have started with a random m and c value, right? You started with a random m and c value. So you got a random m value and c value. Okay, based on this particular m value, you calculated the error. How do you calculate error? For this particular random point, how do you calculate error? You will be calculating by using the formula of your mean squared error. After that, you'll be finding out the slope of that particular point, and then you'll update the MNC value. But how do you update your MNC value? To update the MNC value. So already we understood that. For this particular graph, let me again repeat this point. That is, for this particular graph, if your graph is something like this, where you are talking about your x square equation. If I talk about the x square equation, my graph will be something like this, right? My graph will be something like this. And we understood that the minimum point is here. The error point is here, maybe. The minimum point is here. For this particular graph or this particular curve, the minimum point is here. That is, error point is here. Let's assume randomly you picked your m value here, right? So here in this case, if you're randomly picking the m value here, you should decrease your m value to reach the minimum point, right? If you're randomly picking my m value here, for this particular error, you have to increase my m value to reach the minimum point. Either you should increase or decrease. So the equation for increasing or decreasing or changing the m value is the new m value is equal to the old m value, means you are adding the m value, means right now this is m value, you are trying to increase or decrease the old m value minus some parameter. We'll talk about this particular parameter called as neta, or it is called as learning rate. We'll talk about this parameter in 2 minutes. Then becomes your de by dm. Next your m, or if I talk about c becomes c1 is equal to c naught old c value minus your learning rate into d by dc. So why we are doing this step? What is the main idea of this particular step? Is, as I told you already, either I have to decrease my m value or increase my m value, right? So let me explain you this particular step. Why we are doing minus here? What is the reason for this particular minus? And how this particular step will try to reach the minimum point. Okay. So what happens is, let's assume this is your entire graph of your this one of your x square, that is your error equation, and you know this is your minimum point. This is your minimum point. Okay, this is a minimum point where your error for m value of some, let's assume 1000 or something. We are not sure. It can be anything. It can be m value of anything. Now, when your random m value is present here, I should increase my m value. To reach a minimum point, right? So in order to increase my m value, I should use plus. If I want to use plus, because I should increase my m value from the previous m value, I should do your new m value should be old m value plus something else. Then only you're reaching the minimum point. Whereas, for example, if your slope, if your point is present here, I should decrease my m value to reach the minimum point, right? I should decrease my m value to reach the minimum point. So when I say I should decrease my m value, it should be the new m value is equal to m naught old m value minus something else. Whatever something else, we'll talk about this. Okay. This is my main goal. Right? So when I say I want to increase my m value or decrease my m value, how do we do this then? Let's see that right now. Okay. As we are clear that this is talking about slope of that particular point. d by dm is talking about the slope of that particular point. Okay. Let's assume my point is this, right? My point is this. And we clearly know that when we want to find out a slope of a curve, we'll try to create a line, right? We try to approximate a line which is like a tangent, right? Which is like a tangent. So let me draw a line here, then you'll be having a clarity. Okay, let me draw a line here. Something like this, approximating like this. Right. Just carefully look at this line. Is it looking like a decreasing line? Right. A line, if it is something like this, can I say it is a slope will be negative for this line? We clearly know. Or if we just talk in terms of tan theta, the angle will be something like this, which is ultimately giving the negative values, right? Ultimately, the slope of this particular line will be negative. So at this particular point, or at this particular point, or this particular point, your slope de by dm will be negative. So if your de by dm is negative, that is your de by dm, that is slope of tangent, will be negative, because you can clearly see if I try to approximate a line here with respect to x value, that is with respect to m value, you can clearly see it is negative. It is kind of a negative slope. So obviously your new m value is equal to old m value minus some value into negative of d by dm. It will be negative for sure. So what happens here in this case? It will increase the m value. You can clearly see it is increasing the m value. Means whenever your point is here, as the slope is negative, and when you are doing negative of negative, it becomes plus, and it is increasing the m value. So it is increasing the m value. So in this way, you are trying to update the m value and increase the m value to reach the minimum point. To reach the minimum point, you are increasing the m value, right? In the same way, let's talk about this particular point. Let's take this particular point as an example. Okay, this particular point as example. If I talk about this particular point and try to write the approximation line like this, okay, let me write it properly. It will be something like this, right? It will be like something like this. Means your line will be something like this. More clearly, your line will be something like this. So it's clearly see that you can clearly see that this line is kind of a decreasing line, decrementing line, right? And it will be negative. And for this particular line, it will be positive. When you approximate the slope of this particular tangent line will be positive. And if you just calculate the tan theta also, it will be positive value. So for a positive value, obviously d by dm will be positive, right? D by dm will be positive. So when I say d by dm will be positive, the equation will be as it is. Means new m value is equal to m naught minus neta of d by dm, right? Neta of d by dm. Exactly, right? Minus. So we clearly know that when your slope is selected here, when your m is selected here, we clearly know that we should decrease the m value to reach the minimum point, right? We should decrease the m value. Here we have to increase the m value, we should decrease the m value. So exactly this is the main idea of these equations. So by using the slope of the curve, you're trying to either increase or you're trying to either increase the m value or decrease the m value, ultimately reach the minimum point. Okay. Okay. And moreover, guys, within 3 steps, your algorithm will not complete, because here when you do apply d by dm, it will not identify the minimum value directly, right? It will just go to this point, maybe this point, right? So in order to reach the minimum point, it needs multiple steps. Basically, gradient descent is an iterative algorithm. It's an iterative algorithm. It needs multiple steps to do this. Iterative algorithm means maybe at the first step, slowly it will come here. Second step, maybe it will be coming here. Third step, maybe it will be coming here. Fourth step, maybe it will be coming here. And finally, it will be reaching the minimum point. So the fourth step of this particular gradient descent would be repeat step 2 to 3, right? 2 and 3 until convergence, means reaching the minimum point. So this is the main 4 steps idea of your gradient descent algorithm. So what happens is, in order to minimize this particular equation, that is your MSE equation, that is I is equal to 1 to m y actual minus y pred whole square divided by n. What you are doing, you are trying to apply this step, you are trying to minimize this particular equation by updating the MNC values and finally reach the best MNC value. That is the main idea of this entire linear regression algorithm. Okay. Now in this one term we have not talked about, that is neta, that is n, something like this, right? The neta term. This neta term indicates your learning rate. So learning rate is basically an hyperparameter, guys. It's an hyperparameter which you have to tune or tweak to improve the model performance. It's an hyperparameter. How do you select a learning rate? Generally, how do we choose a learning rate, or what is exactly learning rate means? Let me give a small example here. See, let's assume you're given a task of learning addition, right? You're given a task of learning addition. Generally, let's assume you don't have any idea of any mathematics or something like this. You are just given a task of learning 2-digit addition. How much time do you take to learn addition? Maybe 1 week or maybe 1 day. Let me take 1 day on average. 1 day to learn addition. But if I ask you to learn about integration, at least we need 1 week to understand the entire concept of integration for a normal student, Yes. So for addition, we need approximately 1 day, but for integration, we need 1 week. But why? Why do you think? Because of the concepts, right? Addition is very easy, but integration is slightly complex. The same way works for a data set. For a simple data set, the time needed to learn that particular data set is less, right? The time for your model to learn that particular data set might be less. Whereas if you have a complex data set, right? Time needed to learn that particular data set would be more. So in order to decide the speed of learning process, you use learning rate. Okay. So learning rate is will be mainly, it's a parameter which you have, which in your control, you should change the parameter. No one can tell you what is the best learning rate parameter for your data set. You can just try different values, try experimenting different values. Whichever values works for you, that will become your best value, right? So learning rate decides the speed of learning process. Speed of learning process means how much speed your model should learn learning process. If I ask you to learn integration in 1 hour, what happens? If I ask you to learn integration in 1 hour, maybe you'll be missing many important concepts, right? Or maybe you'll be missing the main important theory behind integration. You just mug up maybe. The same thing happens in your linear regression or in your models generally. If you just give a higher learning rate to a complex model, then your model will not get time to actually capture the important pattern or more important pattern. The same way, if you give a if I ask you, if I give you 1 week of time to learn addition, it is very huge, right? So then it will be very slow in learning process. So when you go when we so let me give a graph of what happens if you're having a high learning rate or lower learning rate. Let me show you. For example, if your learning rate is too high, and you have selected your m value here, and if your learning rate is too low, for example, let us assume too low, then in order to reach your minimum level, your model will be taking very slow steps, baby steps kind of thing, slowly, like this. Slowly it will be coming to the minimum point, very slow, like a baby step, very slow, right? Maybe it might take years to come, or not years, but it will take a lot of time to come to the minimum point, right? So that is the problem if you give a lower learning rate, right? Whereas if you, because you're multiplying by very low value, whereas if you are giving a very high value, then what happens is you're just assume that you're giving a very high value here. So you're multiplying this d by dm with high value, you're multiplying your slope with high value. Then what happens? Instead of reaching the minimum point, maybe it might go somewhere here. For example, if your point is here, might go somewhere here, then it might go away from this particular point graph also. This problem is called as shootout problem in machine learning. Shootout. Okay. So that is the main problem if you give a very high learning rate and low learning rate. So it is not good to give a very high learning rate or very low learning rate. Depending upon your data set and depending upon the complexity of the data set, you should choose your learning rate, right? You should intelligently find out what is your learning rate through various iterations. So this is how the entire linear regression works, and entire how the gradient, and we understood about how to use gradient descent, how to apply gradient descent for linear regression in order to solve the main idea of gradient descent and linear regression. Okay. So right now we have understood this entire thing with help of the simple mathematical understanding, with help of mathematical equations. Now let's implement this exact mathematical equations right now to the gradient descent and see what exactly happens. Okay. So now I told you that your de by dm is the main part, right? We didn't understood about d by dm yet. I mean, what we'll be having in d by dm. In order to solve the gradient descent, we should understand what is d by dm, right? Let's understand this. Now let's substitute the error value in this. What is the error value in this? So if I say e is nothing but what? It is indicate summation of I is equal to 1 to n y actual minus y pred whole square divided by n, right? This is what your e value is, right? Now let me substitute this e value in this equation. Okay, this becomes de by dm is equal to, let me solve this equation and substitute back here. Okay, so d by dm means I told you that we'll be using this slope, right? Right now we are trying to find out slope. You are trying to find out slope. Okay, now let me do like this, d by dm into e value is what, this one, right? So summation of I is equal to 1 to n y actual minus y pred whole square divided by n, right? Now let me take out this n outside and summation outside and put and send this d by dm inside this equation, inside this particular equation. Let's solve this right now. Let's solve this with help of your understanding of your basic, very basic differentiation, whatever we learned in last session. Okay. So if I take out this outside, I can write like this 1 by n. I can also write like this 1 by n summation of I is equal to 1 to n d by dm of y actual minus y pred whole square divided, sorry, no divide by n because already I have taken this outside, divide by n. Perfect. Cool. I can write like this. Now we clearly know that y pred is what? What is y pred? According to linear regression equation, you are trying to predict the y value, right? That is nothing but mx plus c, right? Y pred is nothing but your mx plus c. Y actual is nothing but the actual value of y in the data set. Whereas y pred is nothing but your prediction of your value, that is your mx plus c. So let me substitute mx plus c in this, right? So 1 divided by n, summation of I is equal to 1 to n, d by dm into y actual minus of mx plus c whole square, right? This is what you're getting this after you apply this. Now we'll differentiate this equation and get the final equation for this particular d by dm, right? Let's get the final equation. So equal to 1 by n into. So now we clearly know from our last equation, from our last session, we clearly know, is it looking like something like a square? Can I take this as the entire thing as a and treat it as a square? So we know that according to differentiation rules or differentiation, whatever we learned in the last session, that is dou x square by some or dou x square by x is nothing but 2x, right? Or we can say like this, dou a square by dou a will be something like this, or 2a, something like that, of course, right? Or let me make it more simple to you. Dou a square by dou x may be something like this. Then we can write this equation as, right, 2a into dou a by dou x, right? This is one way, one more. I mean, this is how we can write like this, right? So the same thing I'm doing right now, the same rule I'm using right now, generally the differentiation, that is I'm writing like this: 2 into 2 into y actual minus mx plus c whole square, okay, again into again dou by dou x into y actual minus mx plus c according to this equation, right? According to this equation we can write like this: dou a square by dou x nothing but dou if your a square is having some x term, we can do like this, right? That is what I'm doing right now. Okay, cool. Now from this, what we can do is we can write like this: is equal to 1 by n summation of I is equal to 1 to n 2 into this mx plus c we can replace with y pred because there is not needed. This square is not needed right now. This square will not be there. This square will not be there. Okay. So ultimately you can write this as your y pred. So I can say y actual minus y pred, right? Y actual minus y pred, okay, into dou by dou x into y actual minus mx plus c mx plus c. Again, there is no square also here. You can remove this square part because we have removed it, right? Cool. Now next step, what is the next step? Obviously we should differentiate this part equation, right? This part differentiation is left over. So it is 1 by n into summation of I is equal to 1 to n 2 into y actual minus y pred, y actual minus y pred. So if we just look at this, you can just send this differentiation inside. So we can say dy actual by dx, it will become obviously dm, right? Because we are working with m. So dm. So dy actual by dm minus d. If I send this differentiation again inside, it will be like this: dmx by dm, right, into dc by dm, sorry, plus dc by dm, right? This is how the differentiation equation looks exactly, right? Now if I try to look at this, this becomes 0. Why? Because we clearly know, right? Whenever there is no m term in this particular equation, we clearly know if you have dA by dx, if there is no x term in this particular equation, this becomes 0. So this equation becomes 0, this part becomes 0, right? And also this part becomes 0 because dc by dm, the constant of derivative is nothing but it is nothing but your it becomes 0 because even this part doesn't have any m term, but this part is having m term. And we clearly know, if you just look at this general equation, if you say dou ax of a, it becomes a, right? This is a general rule. So if I write like this, the final equation will be 1 by n into summation of I is equal to 1 to n 2 into y actual minus y pred maybe high into minus of xi, right? Where I indicates this y actual I minus y pred I. Okay. Now if I want to write the final equation, my final equation will be like this. I'll be getting the I've solved this derivation is gone right now, and finally the equation will be something like this. If I get this minus outside, so minus 2 by n into sum of, that is summation of I is equal to 1 to n xi into y actual minus y pred. This is the final equation for dou E by dou M. That's it. This is a final equation for dou E by dou M. Simple, right? Now, if I do it for dou E by dou C, exactly same thing comes, but the only thing is in the last part, your dc by dc will be remaining because you're doing dou E by dou C here right now. You're doing dou E by dou C. So last dou E by dou C becomes 1. So what happens is the final equation will be something like this: minus 2 by n into summation of I is equal to 1 to n y actual minus y pred. Because obviously here in this particular term, there is no x, right? There is no d by dm. So it becomes dou mx by dou c, which becomes 0 here. Okay. So ultimately you'll be getting this particular term for dou E by dou C. So these are the main final equation which should be substituted back in this particular equation. That is nothing but your m, old m value is equal to new m value is equal to old m value minus of learning rate into dE by dm, right? Then new c value is equal to old c value minus learning rate of dE by dC. So this dE by dm and dE by dC will be substituted back here, and finally we'll be getting this one, right? This is the entire linear regression. So we have completed the entire linear regression equation and the entire linear regression problem right now with this particular things. Okay, so we have started with what? We have started with this particular simple equation, that is y is equal to mx plus c. Y is equal to mx plus c, where you are trying to find out a line, for a given points for a given data set, best fit line. So in order to find out the best fit line, you are trying to find out the best MNC value. So in order to find out the best MNC value, you need to find out the line which is having the least deviation. Least deviation means the least error, least MNC value, that is y actual minus y pred divided by n. So when I say least MNC value means minimum MNC value. So in order to find out the minimum MNC value, you need to use something called as gradient descent approach, and the gradient descent works under the principle of differentiation. So we use applied gradient descent, where we understood that gradient descent is an iterative algorithm, and you're trying to start with a random point, then you're trying to find out a slope of a curve, and you're trying to either increase the m value or decrease the m value, or either increase the c value or decrease the c value, and finally find out a minimum point, which is reaching your minimum line, right? So ultimately that is how it works, and learning rate is nothing but a hyperparameter to decide the speed of your learning process. So this is regarding your entire linear regression. So right now in this video, we just solved how exactly this linear regression works with help of the equations and mathematical understanding of that. In the next video, we'll implement this everything from scratch. When I say from scratch, we'll not be using any library. We'll try to apply the exact equation through using your Python code, and we'll try to solve the exact thing whatever we have done using your Python code. Okay. So I hope you got this point and how to understand this linear regression from scratch, right? So if you like this video, please like it, share it, and comment your doubts or comment about how do you like your videos, and subscribe to my channel for more upcoming videos like this. Okay, thank you guys.